So next we're going to start section 7.5, which is on linear programming applications. These are basically just the word problems that correspond to linear programs. Before we actually get started on this set of notes, there are two comments that I want to make. The first is that I think it might be a good idea to just keep section 7.4 pulled up in front of you as you go through these videos, just because if you're not already familiar with the procedure, it might be good to have all of those procedures in front of you just so that you can reference them as we go through the video, because I will be going through the steps quickly. I'll try to explain the first few times that I take each of the steps, but still it might be good to just have those lists in front of you. And then the second comment that I wanted to make is that in today's videos, I am probably going to either really quickly go through the row operations or omit the row operations and mostly just focus on the new stuff, which is setting up the linear programming problems and then going through the linear programming procedure. I'm going to skip or sort of glance over the row operations for a few reasons, but if you are a little bit shaky on row operations still, then what I would recommend is just that anytime we're about to do a row operation, you just pause the video and work it out for yourself using some scratch paper, and that way you can get a little bit extra practice with it. But because we did row operations essentially all through Unit 3, and because I think that they're not especially enlightening relative to the amount of time that they take in a video, I'm going to mostly skip over them. So let's look at this first problem here. So this is typical of what you might see for an applications problem in linear programming. It says an office manager needs to purchase new filing cabinets. He knows that this certain kind of cabinet costs $40 each, requires 6 square foot of floor space, and hold 8 cubic feet of files. And then there's a second type of cabinet called the Excello cabinet that costs $80, requires 8 square feet of floor space, and holds 12 cubic feet of files. And then we have these budget constraints. So the budget permits no more than $560 to be spent. And then the office has room for no more than 72 square feet of cabinets. And the manager wants to figure out how much storage space he can afford given those constraints. So our goal is just to set up first the linear program, and then we'll decide how to optimize and find the best storage capacity that we can manage. So first of all, I think it's a good idea to decide what your variables are. Usually your variables are going to be the things that you're actually looking for. So here it says how many of each type of cabinet should we buy. So I'm going to let the number of ACE cabinets equal X1, and the number of Excello cabinets that we're going to buy will be X2. So it's a good idea to just let the things that you're looking for be your individual variables. And then we can decide what it is that we want to optimize and then what our constraints should be. So usually I like to start with the thing that we're trying to maximize. So we want to maximize the amount of storage space that we have. Just to keep with the variables that we used last time, I'll call this first one Z, but you don't necessarily have to call the objective function Z. You could call it whatever you want. So we're going to maximize Z equals this thing, and in this case, this objective function corresponds to storage space. So I want to write down an expression for the amount of storage space that we'll get given this number of ACE cabinets and this number of Excello cabinets. So if I look for the amount of storage space that we get, it's 8 cubic feet of files per ACE cabinet and 12 cubic feet of files per Excello cabinet. So the way that I would write down an expression for that is we would have 8 cubic feet of files per ACE cabinet with X1 ACE cabinets, plus 12 cubic feet of files per Excello cabinet times the number of Excello cabinets, and therefore this expression tells us the total amount of cubic feet of storage space that we get. And then next in a linear program, we're going to have some constraints. Usually that's just written as subject to this list of constraints. And again, I like to, on word problems, just label what each equation actually means. So let's write down an equation which refers to our square footage constraint. So notice that the office has room for no more than 72 square feet of cabinets. So that's like the square footage on the floor where we're able to store these cabinets. We can use no more than 72 square feet of that floor space. And we know that ACE cabinets take 6 square feet of floor space each, and Excello cabinets take 8 square feet of floor space each. So the way that I would write that constraint is like this. Remember that in these constraints, we want our variables to be on the left side and then the inequality to face the right side with some constant on the right side. So I would write that like 6 square feet of floor space per ACE cabinet times that many ACE cabinets, plus 8 square feet of floor space per Excello cabinet times the number of Excello cabinets. So the expression that I've just written, this expression, is the total amount of square footage that we need for our cabinets, and that has to be less than or equal to what the office actually has, which is 72 square feet. So this is an inequality because we don't actually care whether we use the entire 72 square feet of floor space. It may be that we can only fit in so many cabinets, or maybe our budget is too tight to actually use all of the floor space. We're just trying to maximize this objective function, but we do have to be subject to this constraint. But we're not necessarily going to use all 72 square feet of floor space. And then we also have this budget constraint. Our budget constraint is that we're going to spend $40 per ACE cabinet times the number of ACE cabinets, plus $80 per Excello cabinet times the number of Excello cabinets, and that can't exceed our budget of $560. Okay, so this is what we get whenever we put all of this together, and we also have a non-negativity constraint in all linear programming problems. We're always going to assume that x1 and x2 have to be bigger than or equal to 0 because they're supposed to be some sort of physical quantities. So in this case, they're the number of cabinets. I can't buy a negative number of cabinets. So of course we have this constraint. So now we've set up the linear program. The next step is to transform this into an initial simplex tableau, and then we'll go through the procedure to solve this problem. So I am going to delete what I've written here. I scribbled over it a second ago just to sort of compactify things. But remember that each of these constraints that I wrote down and also the objective function, they all have these meanings, a storage space, which is what we're trying to optimize, and then we have these constraints for the square footage and budget. So I'm about to delete this. On the notes that I'll post online, I'm going to be posting some separate handwritten notes. So if you want to read over this again more carefully, then you can. So here is the linear program that we just found. And now we're going to solve this linear program. Remember that our first step is to take each of the inequalities and rewrite them so that they have a slack variable, because we want to turn them into equalities. So we introduce the first slack variable for that first inequality, and then we'll introduce a second slack variable for the second inequality. It is important that these slack variables are different, so each inequality will get its own slack variable. And remember that we also want to take our objective function and rearrange it so that all of the variables appear on this left side. So we would have a negative 8x1, minus a 12x2 plus a z is equal to 0. So that will become our objective row in our initial simplex tableau. So now we're going to set up the simplex tableau. For my initial simplex tableau, I normally like to label the columns, but you don't have to continue labeling the columns. I'm also going to do something a little bit different today, and I'll show you what it is in just a second. So maybe I'll start by just filling in what this left side is for the simplex tableau. So here what we have is a 6, 8, 1, 0. As I start to translate that first equation, and then my second constraint equation is going to be a 40, 80, 0, 1 as my coefficient on S2. And then for this last row, my objective row, I'm going to have a negative 8, a negative 12, a 0, and a 0. And then if we were abiding by what we did last time, then we would have a z column and then a constant column. And remember what I mentioned last time is that the z column, if you did keep it in this matrix, would always be 0, 0, 1, and then at the end of the problem, whenever you translate this into an equation, you'll always just get the equation z is equal to whatever number is down here. So if there was like a 78 down here, then z would equal 78. So what we're going to start doing as a shorthand is I'm going to delete the z column altogether. So we're not going to include that z column because it would never change. And instead, I'm going to identify z with this bottom right entry. So anytime I read off this from this matrix, the value of z, z is just going to be this bottom right entry down here. And otherwise, in this column, I'm just going to record the ordinary coefficients like we have been doing earlier. So this would be 72, this would be 560. I know this is a little bit strange because these coefficients are technically the coefficients on the right side of the equal sign over here. They don't actually refer to z. Well, most of them don't. But this bottom right one can be identified with z. So this is just sort of a compactification that we can use. It's okay with me if you want to continue using the ordinary z column, but this will just prevent us from having to do some extra writing. This is also the notation that your book uses in case you use that for a reference. So for that reason, we're going to stick with this notation. So this is our initial simplex tableau. And next we need to decide how to eliminate these negative indicators. So remember, the goal whenever you're trying to optimize something is to eliminate first all of the negative indicators, and then once the negative indicators are gone, we'll just read off the solution. So I want to get rid of those negative indicators, and for that we go through the pivoting procedure. So if you want, you can pause the video and pull up the procedure for pivoting, but I'll talk you through the strategy. Remember that to choose the pivot column, we choose the most negative indicator. So wherever the most negative indicator is, in this case it's the negative 12, that's what we want to attack first. So that will be our pivot column. And next we'll look for our pivot row. Remember that to decide the pivot row, we're going to compute these quotients. So I like to write Q for quotient, or you can just put quotient here. And the quotient is going to be the far right value divided by the value, divided by the value in the current column. So the first quotient that we would compute would be 72 divided by 8, and that would give us a 9. And then the second quotient that we'll compute would be 560 divided by 80, which will be 7. And again, we're going to be choosing the leftmost number or the least number of these. So just like we chose the negative 12 because it was the smallest, or the most negative, we're going to choose the smallest number here, and that's going to represent the row where our pivot lives. And that means that if I look at the intersection of that row and that column, we've found our pivot. So the pivot is going to be this 80. And now the procedure is to take that 80 and turn it into a 1 by using the division row operation, and then we want to eliminate the rest of that column like we normally would with Gauss-Jordan elimination. So my first step is just going to be that I'll take row 2 and divide it by 80. So I like to do that as its own row operation. That means we're not going to be changing these top and bottom rows. So I like to go ahead and write them down. The middle row, however, is changing. I'm dividing by 80. So I would get a 40 divided by 80, which is 1/2, 80 over 80, which is 1, 0, 1 over 80, and 560 over 80, which is 7. By the way, 560 over 80 is the quotient that we computed a second ago. So that quotient is always going to end up being that right entry there, if you want to use that sort of shortcut to save you some time. So we know that that quotient in that far right entry will end up being a 7. Okay, so this is the new simplex tableau that we get. And now we have a 1 where we want it, so we want to use that 1 to eliminate the rest of that column. So I would take row 1 and subtract 8 times the pivot row, and then I would take row 3 and add 12 times the pivot row. And that'll give me this new simplex tableau, which is going to be, so if you'd like, you can just trust me on these. I think in order to keep the video at least a little bit shorter, I'm just going to speed through these, but you can feel free to pause the video if you'd like as we go through them. But just be a little bit careful. If you need to do some scratch work in order to compute some of these entries that involve fractions, then that's totally fine. So, for example, in this first one, we're taking, let's look at this top entry over here. So that we're taking row 1 minus 8 row 2. So that would be a 6 minus 8 times 1/2. So that would end up being a 6 minus a 4, which should be a 2. But if you're not comfortable with working with fractions like that, then feel free to just take the row operation that you're performing and do some scratch work over here. And then you would end up getting this 6 minus 4, which is 2. And that's the entry that should go here. So if you need scratch work for individual entries, that's totally fine. Often in today's setup, I'm just going to be reducing fractions on the fly. So if you want to just sit back and trust me whenever it comes to row operations, that's fine with me. You don't have to worry about keeping up with the row operations. You can just believe me that this is what you get after doing those row operations. But what I would recommend whenever you do this on your own is that you either convert these to decimals if you want to be using a calculator, or you at least leave them as unreduced fractions, because then most of the time the fractions that you'll be dealing with will have the same denominators. That'll make them a little bit easier to handle. So you don't necessarily want to be reducing the fractions as you come to them. However, in my work, I have reduced the fractions just to keep them a little bit smaller. Okay, so anyway, what we get as the end of this set of row operations is this matrix. So I'm just going to copy it down real quick. And now we have eliminated the entries in the pivot row that we wanted to. So we should get a negative 2, 0, 0, 12 eightieths, and 84. So this is where we are now. And notice that our pivot column is now fixed. So we're happy with the pivot column. We have the one where we wanted, and we've zeroed out the rest of that pivot column. And if you'd like, you can keep writing this bar to divide the objective row away from the constraint rows. But unfortunately, we still have a negative indicator. So notice we have a negative indicator here. It's this negative 2. That's the only negative indicator. So that means that will be our pivot column. And now we look for these quotients. So we would have a 16 divided by a 2. That gives us a quotient of 8. And then be careful with this one. This is a 7 divided by a 1/2. So remember, when you divide by a fraction, that's the same thing as multiplying by its reciprocal. So that would be a 7 times 2 over 1, which is 14. So this quotient would be a 14. We'll take the smaller of the quotients. That will tell us where our pivot lives. So that 2 is going to become our pivot. And if we want that to become our pivot, then we need to take row 1, the pivot row, and then divide it by the pivot. So we'll take row 1 and divide it by 2. And I'm just going to take this and copy it down onto the next page. So I'll just show you what happens when you divide that top row by 2. Notice that in this fourth entry in the top row, in this entry here, we'll be dividing by 2. So that would be a negative 1/10 divided by 2, which should be negative 1/20. So that's the entry that we'll get there. Otherwise, these entries are pretty easy to divide by 2. So what we end up getting after that row operation is, we'll get 1, 0, 1/2, negative 1/20, like I mentioned a second ago, and then 8. And then the other rows did not change. So the other rows will still look like this. So now we have the one where we want it. That's an 80, 84. So now we have the one where we want it. We're just going to use that one to eliminate the other non-zero entries in this column. And to do that, I need to take row 2 and subtract 1/2 times the pivot row, because I'm trying to kill that 1/2. And then I need to take row 3 and add 2 times the pivot row, because I'm trying to kill a negative 2. And the result of those row operations is this. We'll get a 1, 0, 1/2, negative 1 over 28, because we didn't change the top row. But these two rows are going to change. We'll get a 0, 1, negative 1/4, 3 eightieths, and 3. And then we'll get a 0, 0, 1, 4 eightieths, 100. So notice that here I decided not to simplify something like 4/80ths, just in case we needed to do any extra row operations. I just wanted these to have the same denominator, but you can simplify them if you'd like. So now we're actually done with the simplex method because we don't have any negative indicators remaining. So now the goal is just to read off the solution. And for that, I like to label the columns again. You don't have to do this, but it might be nice. So this will tell us what each of the columns stands for. Remember, I'm identifying Z with this bottom right entry. So Z is going to equal 100 here. That would be the max number of storage space that we have. And that was actually in cubic feet of storage space. So that's the optimal amount of storage space that we can get. And then if we wanted to actually answer the question, which was how many of each type of cabinet should we buy, remember X1 represented the number of ACE cabinets and X2 represented the number of Excello cabinets. So we'll read off from this matrix what the values of those are. In order to read off the values, remember that what we're going to do is we delete any non-basic columns. So this is a non-basic column and this is a non-basic column because they have more than one non-zero entry. And then you translate the remaining equations here. So if I translate the top line, it would say x1 is equal to 8. If I translate the second row into an equation, then it would be x2 is equal to 3. And this tells me the number of each cabinet that I should get. So I should get 8 ACE cabinets and 3 Excello cabinets. And that will give me the most storage space given the constraints on the budget and the square footage that we have for storing these. So that's the full problem here. Don't worry too much about the row operations. The main thing that I want us to focus on for today is just the new techniques. So first, being able to set up the word problem as a linear program, and then second, deciding which row operations we need to be doing. So if the row operations part was too confusing to you, or if you need to familiarize yourself with the procedure again, then feel free to just pause the videos now and then head over to the previous section of notes where we talked through those in a little more detail.